Hello and welcome to Physics Lesson 3.05, Part 1, Motion with Two Equations. This does not correlate to the 3.05 homework assignment. 3.05 in the homework assignment is a second part of vector word problems. But what we're working with here is what do we do when we begin to make the shift from working with kinematic problems in one dimension to two dimensions? So anytime we have two different types of motion, we have to have two equations. So one of the classic examples is a cop chasing a speeder, and you have an equation of motion for the cop, and you have an equation of motion for the speeder, and you have to use those two equations to solve a problem. In our case, we're looking at something a little bit different. You guys are fed up with physics, and you have come up with a way you think to see if I can get this any brighter. Doesn't look like it. I'm going to try it focus. The way to take me out so that physics is no more. What we're going to want to do is almost always just start with a diagram. So I'm kayaking down the river on my Saturday morning trip. And Maggie is up on the bridge. Why Maggie? Well, she seemed like the least likely. She drew the short straw. And we've got 15 meters from the top of the bridge down to the water. Actually, down to the top of my kayak. So here we go. Maggie's up here with her bowling ball. The class is standing behind her. Cody's got the calculator. He's crunching the numbers. Here's my kayak coming down Blanchard. Got paddle here. Got paddle here. All right, you guys marked out 1 meter marks so that you can kind of tell, and you use that to determine that my velocity is 14.3 meters per second. River's really clipping along today. All right, so anytime we're working with equations of motions like this, each portion must have its own equation. That's rule number one. Number two, we'll get to that. By the way, I forgot to say that this is constant. So my speed isn't changing. I don't have any acceleration. So we're going to want a variable bank for me, and we're going to want a variable bank for the volleyball. So let me do B sub O, B sub F. I'm just going to do X, A, and T for me. And over here for the volleyball, let's do, or for the bowling ball, B sub Y, B sub final Y, Y sub O, Y sub F, A, and T. And let's make our coordinate system traditional. Well, let's start off with me in my kayak. So if I'm going at a constant velocity, that means when I start off, I've got 14.3 meters per second. But what does that mean about my velocity at any other point? Take a second to see if you can figure out what the implication is for the fact that I have constant velocity. You can pause the video if you want to. Hopefully you saw that if my velocity is constant, I have one value and I don't have any acceleration. So all of my variables are V, X, and T. So I'm going to put in 14.3 meters per second. For my volleyball, why do I keep calling it a volleyball? A volleyball wouldn't hurt so bad. For my bowling ball, I'm starting off at the 15-meter mark. Let's make the top of my kayak 0. Because remember, the kayak's got a few feet, so I can't actually make it down to the top of the water, or that'll throw off my calculation. So I'm starting off at the 15-meter mark, and I'm going down to the 0, and this is going to be negative 9.81 meters per second squared. I know my initial velocity is going to be 0. What I want to solve for is how far away. So as I'm coming down, when Maggie drops the bowling ball, it's going to take a certain amount of time. And what we want to happen is we want at the time, whatever time it takes to go for these 15 meters, is the time it's going to take for me to go from here to here. So we need the intersect point to be here. So the implication is that the time that's traveled here has to be the time that's traveled here. And you'll see that this is often the case, that time is the variable that ties the two equations together. Ties the two equations together. So what I'm going to do is I'm going to solve for time on this side, and then I'm going to loop it over, and I'm going to see how much of a distance it takes to travel. And this is what you guys did, and you came up with 23 meters. So I'm going to do y sub f equals y sub o plus v sub o t plus 1/2 at squared to solve for time here. So that's going to give me 15 is negative 4.91 t squared. This is 0, so these terms go away. And when I solve for time, I end up with 1.74 seconds. Well, if it takes 1.74 seconds to drop from here to here, then I need to make sure that I've traveled 1.7, I need to come out 1.74 seconds. And whatever distance that is, when I travel that distance, that's going to put me at the intersect point at the same time. So I'm going to bring 1.74 seconds over here. Well, this is a little bit simpler equation because I have just velocity, displacement, and time. We know velocity equals displacement over time. So if I take 14.3 equals x over 1.74, I end up with negative, let's see, I get the negative. Well, it would be negative because if this is 0, that would be negative direction, negative 25 meters. So it turns out that you guys, when you dropped it, so if I was 25 meters out and you dropped it when I was 23 meters away, you're going to miss me. It's going to land on the either on the back side of my kayak and sink my kayak, or it's going to miss my kayak altogether. Turns out you didn't have your kinematic equations calculated correctly, so it's probably good. I'm going to stick around and we're going to do a little more physics to help you get a little bit better. And maybe it splashed behind me and I didn't even notice it, because it would be really awkward when I come back if I had to, discuss the whole, attempted murder plot. Okay, that's just talking about what do we do when we've got these two different types of motion. And this is setting us up for really going into what we call projectile motion, which is going to be part 2 of 3.05. All right, so go ahead and roll into part 2 now, and thanks for watching.